Okay, so our first unit is on electric charge. You can find this in section 5.1 of the textbook. Electric charge comes in two kinds: positive charges and negative charges. Positive charges are mostly in the form of protons, while negative charges are mostly in the form of electrons. Protons and electrons are constituents in atoms. Protons live inside the nucleus, whereas electrons live inside orbitals around the nucleus. Because of the nature of the nucleus, the protons are much more tightly bound, so it's very difficult to remove a proton from an atom, but relatively speaking, it's very easy to remove an electron from an atom. Generally speaking, when you do remove an electron from the atom, it's going to be the outermost electron, which is usually referred to as the valence electron. Ions are atoms which have basically either lost some of their valence electrons or they have gained a few extra electrons. Examples of ions could be, for instance, the hydrogen ion, which would just be a single proton, or the sodium ion, which is positively charged, or the chlorine ion, which is negatively charged. Ionization is the process of turning an atom into an ion. So ionization would be either a situation where maybe I'm bombarding an atom with radiation to eject one of the valence electrons out of it, or I am bombarding a material with a beam of electrons in the hope that the material will pick up some extra electrons. And there's a whole host of ways that you can ionize atoms. Generally speaking, it's going to take some energy to do it, because the most energetically favorable state under normal conditions would be for the atoms to be neutral. Charges exert electrical forces on each other, and we usually call this the electric force. And it follows some relatively simple rules, which we'll learn in more detail later. Basically, charges will be repelled by each other if they're the same type. So positives are repelled by positives, and negatives are repelled by negatives. But if charges have opposite types, like one is positive and one is negative, then they'll be attracted. The strength of this attraction or repulsion depends on how close they are. So the closer two charges will be, the greater the effect will be. In particular, this is called an inverse square force, because the force decreases with the square of the distance. That means if I double the distance between the charges, the force gets divided by 4. We measure charge using SI units, and the SI unit for charge is the coulomb. Coulomb was a particular scientist who did a lot of research on electric charge and the nature of the electrical force. Coulombs are usually denoted with a capital C, and the current definition of the coulomb is in terms of the charge of a proton. Historically, this wasn't always the case, but in 2019, the SI units were revised to change the definition of a coulomb so that it would be based on a more fundamental unit. So E is used to represent the elementary charge, and this is the amount of charge that a proton or an electron will have. A proton has a charge of positive E, and the electron has a charge of negative E. Before the redefinition, in terms of the old definition of the coulomb, the elementary charge was measured to be 1.602176.634 times 10 to the negative 19 coulombs. Because of the 2019 definition of the units, the elementary charge is now defined to be exactly 1.602176.634 times 10 to the negative 19 coulombs. And what this effectively serves is a definition of the Coulomb now instead of the elementary charge. So if we stipulate that the elementary charge is 1.602176.634 times 10 to the negative 19 coulombs, then that tells us what a coulomb is, because if we can figure out how many charges we have, and then use this definition to figure out how many coulombs that will be. And because of how insanely precise this number is, changing the definition doesn't actually change any of the actual scientific results. Because the experiments were careful enough and precise enough and accurate enough that none of the numbers you get when you do other experiments will be appreciably different to that level of precision. Okay. The triboelectric effect is an effect that happens when you use friction to rub two different types of materials together. And essentially this is what you might experience in your ordinary daily life as static electricity, right? So everybody knows that if you're in cold weather and you rub your shoes on the carpet and then go and touch the doorknob or your cat or whatever, you're going to get a zap, right? There's going to be a spark. And that spark is there because when you rubbed your shoes on the carpet, you exchanged electrons with the carpet. The triboelectric effect is a general name for this effect that when two materials are rubbed together, they can exchange electrons. One of the materials is going to have a tendency to gain electrons in that interaction, and the other will have a tendency to lose electrons in that interaction. And the reason that one will gain and one will lose is really based on the detailed chemistry of those objects. It's somewhat related to the concept of electronegativity, if you've ever heard of that concept from a chemistry class. There is a series that tells you which types of materials will gain electrons and which types will lose electrons. It's called the triboelectric series. And you will learn about that in one of your virtual labs this week. And the triboelectric series is basically just a list of materials from more positive to more negative that tells you, if you rub one material with another one, which one is going to gain electrons and which one will lose electrons. Notice that we're not talking about gaining or losing protons, and that's because you really can't remove a proton from the nucleus through friction. So whenever we're talking about macroscopic objects gaining a charge, we're always talking about a charged object either having an excess of electrons or a deficit of electrons. Okay, so a positively charged object that's macroscopic, like person-sized, that will have a deficit of electrons. It'll have less electrons than it needs to be neutral. And a negatively charged object will have more electrons than it needs to neutralize its protons, and so it will have a little bit of excess negative charge. Most objects are electrically neutral, which means that the number of electrons and protons are equal, and this is because of the forces electrons and protons exert on each other. Right? Because positives and negatives are attracted to each other. Electrons have negative charge, protons have positive charge, and that attraction causes them to tend to sit right on top of each other, resulting in a situation where the net, or overall charge, is neutral, or zero. Okay. Local conservation of charge is a law of nature, and basically it's relatively simple. The statement is essentially that within a closed system, the total or net charge is constant. So in a closed system, an object is not going to change its charge spontaneously. The only way the net charge of a system can change is if you bring some charges from outside into the system, or if charges that were in the system leave it. Okay? And so this concept is basically that the total charge of a system can only change by bringing charges in or taking them out. Now, I do want to be clear on what this does not say. This does not say that electrical charge can't be produced spontaneously. So there are certain interactions that can occur where you can create charged particles from a neutral particle, or you can create a neutral particle from charged particles. The simple example of this is the annihilation of an electron with something called a positron. So electrons are negatively charged, and the positron is the positively charged antiparticle to the electron. And when a positron and an electron meet, they annihilate each other and produce a photon. The photon doesn't have any electrical charge. The electron has a negative electrical charge, and the positron has a positive electrical charge in the same amount. In this case, charges were destroyed, but the net charge still did not change, because before the net charge, before the interaction, the net charge was 0, because we had a unit of negative charge and a unit of positive charge, which adds up to 0. After the interaction, the net charge is still 0, because the photon doesn't have any charge. So in this case, you have charge being destroyed, but the net charge didn't change. Okay? So the upshot of the local conservation of charge is that charges can be created or destroyed, but if they are created or destroyed, it always has to be done in such a way that the net charge, or the total charge of the system, does not change. Alright, let me get rid of these colors. Alright. And that, I guess, is my talk.